All right, so welcome to Informal XICC. We're just today I quickly wanted to show you some of the measurements and data considerations that you have to do when you're working with atmospheric caps. Every now and then you may have sample environments that can't survive going into vacuum, or you may have samples that don't do well in vacuum, and so in those cases, you can separate the sample environment, sample chamber, from the rest of the system, which would then be under vacuum. The drawbacks are, of course, that in that sense, or in that case, you will have both absorption and scattering from the air that's around the sample. And in addition, in order to isolate the two or separate the two, you will need to have Kapton windows in between them. Now, what we have here is the demo lab system in the US, where we have put in a standard sample plate with the atmospheric caps. And there are two parts to that. On the left-hand side, there's a tube, and at the end of it has a see-through Kapton window. And on the detector side, there's a section with a larger window, and then, of course, a mechanical a fixture to ensure that the vacuum on the detector side is not breached. So anyway, going into that and setting that up, that's a different discussion. What I want to show you here is some of the consequences of running in that setup. On the right-hand side, we see the normal sample view, where you can see that in fact we can still see the sample plate. D4 is there, and the beam looks to be going through the center of that. However, we don't see as much of the sample plate as we normally would, and that is, of course, that we're looking through that tube that is on the incident side. And so we're only looking through that tube in the window and through the Kapton. Kapton is also coloring the whole thing a little bit yellow. And so that's essentially what we have to work with. So it's nice that we can still see the sample plate. We just don't see as much of it as we did before. Now, we can still operate, of course, with XICC and data analysis and all of that sort of stuff. I just want to take a couple of measurements to show you some of the features that you will see when you operate in atmospheric caps. So the one thing here, I just take a notice. I'm going to take a brief measurement. I'm in max and standard configuration, and I'm going to measure that for, let's say, 15 seconds here. So a fairly short measurement. It's sort of obvious that when we're working in with an atmospheric cap, we can't bring the detector all the way up to the sample. So there's no possibility to go into wax. If you do press wax, I think the detector will try to move as close as it can, but it'll essentially be similar to what we have in max. All right, so I've saved this. This is just completing right now. I'm going to go into my program here and find the directory where I'm saving this. This would all be in here, and I have my data right here. So this is in linear right now. We have, as normal, we would have the direct beam. We have some tails of the direct beam, and then we have a fairly high level of background, which is, again, scattering from the air, scattering from the Kapton, and we can also see a Kapton, slight Kapton peak here just going over the background in the system. Again, I have no sample mounted here. This is just going directly through the hole. Now, then if I just look at this Kapton here again, we can see it's at between 0.3 and 0.4. This is not accurate for a Kapton because this is the Kapton that is on the window, and of course the window is not in the same position as the sample is. So that will have been shifted from where you'd say ideally you'd expect the Kapton. Now, what I wanted to show you is if we go to something that has a larger window. So this was a fairly small, let's say, sample hole, and anything that would be scattering from the first window would in some max region be blocked by the actual sample holder. If I go to this next position here, where the hole is a lot larger, you'll actually see that we're able to see two Kapton rings, one from the first and one from the second. Let me actually do that. We'll make a 15 measurement. Let's just put here large hole, and And then I'll just measure that for 15 seconds and we can do a quick comparison. Go here now, of course, it's not, this is not a huge peak. And again, it doesn't rise a lot above the background. So there's quite a bit of noise in here. For samples that scatter strongly, it won't be a problem. For samples that scatter weakly, that additional bump or that additional background in general could in fact be a problem. Now we have the second data set done. Let's take a look and throw that into here. So what you can see here is that there is actually a slight additional peak over here. This is the peak from the Kapton window that is closest to the detector, and this is the peak from the Kapton window that is on the other side of the sample. Both of these, of course, are something that will affect your data, and subtractions is something that you have to keep in mind. In general, you could say that the smaller the hole that you can be going through, or the more restricted it is, the less you'll see from that first Kapton window. As a corollary to this, you could also say that any specific shape that your sample holder has, dog bone or any kind of other shape, would actually result in a shadowing, or could result in a shadowing, as the radiation from that first Kapton window could be blocked differently by your sample holder. So that's just something to consider, that if you see some strange shadows in your two-dimensional data, that you could in fact be seeing a shadowing effect. We can just quickly take a look and see what the two-dimensional data looks like. Nothing much here. If we change the dynamic range to something that, okay, there we see, and we see some slight increase in the intensity around here. If we go to the second image, I'm not sure that we can see both of those. We may be able to. There's a slight indication of two rings here, one here and one here, but it's very, very slight. And again, the general radiation background is quite high. Let me just see here. I think that's basically what I wanted to say. We can just quickly go and take a quick measurement from a strongly scattering sample, the silver BN8, and just show that in that case, those windows really don't matter. Again, if you have weak scatterers, then they will matter, and you do need to take into account the, let's say, think about how you make your sample holder and how you do your subtraction, so that you don't get spurious effects from having this additional background level in your system. I'll finish off by just taking a look at this image when it's done. Let's go back and look at the 1D image. Here we go. And we can take the different data sets up, all three of these. Let's see this one. And let's bring all of them over there into the setup here. And what you can see again, that the major thing that we would be looking for in the silver BN8 would be the peak locations. And really, this background level, although it does add to the overall background in the image, doesn't affect the major conclusions of our conclusions on the silver BN8. So I think with that, that gives you a quick intro to the things that you'll need to be careful of and observe when you're using the atmospheric caps. And with that, I think I will close down this presentation. Thanks.